Here we go. Okay, so we're in chapter 12 now, okay? I'm not sure, I think we might have gotten past this slide, but in the other class we didn't before I began the lecture. Their lectures for today, I mean. So I figured it'd be good if we start at the same spot as them, which is that here. So again, in this chapter, what we're doing is we're looking at normal distribution, okay? That's what we're looking at here, the normal distribution. You know, it is one that occurs very frequently. That's why it's studied a lot. And let me see what I was going to say. Yeah, okay. You know, there's a lot of very nice features about it. For instance, it's symmetric about its mean. It is bell-shaped, just to name a few very nice properties. Another one is actually given, excuse me, by this rule that we have, the empirical rule, as it's called. So here, in a normal distribution, what they're saying is about 68% of the data values, they're within one standard deviation of the mean. In other words, if you're at the mean, right, of the normal distribution, we'll see some graphs. We saw some graphs last time. We'll see some more graphs today. And if you go one standard deviation to the left, in other words, you subtract one standard deviation from the mean, and you add one standard deviation to the mean, so you go one standard deviation to the right, you'll have about 68% of all the data values. You'll have about 68%. If you actually add and subtract two standard deviations from the mean, you'll obtain about 95% of the data values. And if you add and subtract three standard deviations from the mean, you'll have about 99.7% of the data. We'll see some examples today that will make this a little more clear. It's just telling you that most of the data will be within three standard deviations of the mean. That's what they're basically saying. Most, if not all of the, well, not all the data, but most of the data will be between within three standard deviations of the mean. And this textbook thing, that's really for me. Let me just show you the picture. They have a picture in the textbook. Wait, I gotta share that actually. So let me stop sharing this. I did email the notes, so the notes here you should have. Let's get to the, here it is. Okay, now let me get to that page. Here it is. So this is really what they're trying to say. It's what's on this page. Again, you could zoom in a bit. You have zoom controls on the left. And hopefully everyone, I hope everyone here can see. Okay. Everyone here can see what's happening. So again, you can see that if you go within one standard deviation to the left and one standard deviation to the right, so if you take the mean and subtract a standard deviation and add a standard deviation, you can see that about 68% of the data you will have, 68% of the data falls within a standard deviation from the mean. That's really what we're trying to say here, what I'm trying to say here. Moreover, if you add and subtract two standard deviations, so if you go two standard deviations to the left and two standard deviations to the right, you have like these bounds, as you can see, that will contain 95% of the data. That's what this will contain. Okay. That's what they'll contain. And same thing with the 99.7%. That's 3 standard deviations. The little circle here that you see, that's actually the Greek letter sigma. I think I presented that last time. And it's just notation for the standard deviation. That's all. I figured it'd be good to present the pictures here because they illustrate really well this empirical rule, what they're trying to say. So that's what the empirical rule is. I mean, we really need rules like this and technology like Desmos and stuff later we'll see, such as z-scores, mostly because we don't have all the data in front of us. It's not like, in other words, in chapter 11, the previous chapter where we had all the data listed, whether through a frequency table or just listed as a list. Here we don't have that. So we need certain rules like this to help us see where most of the data is, what data is more likely to happen than another, that kind of thing. Okay. So this was from the textbook. So again, I'm not going to, keep this up much longer. The textbook, again, it's free and it's on, Lumen Learning. So let me stop sharing this. Let me get back to the notes. Again, the notes, I did email, so you have them. Okay. Let me get to this page. Okay, so now we're going to go to page 2 here. And here I'm just going to do an example, and then I'll have everyone try one. And it's really just demonstrating, well, maybe not demonstrating, but it's just applying, that's better, the empirical rule. And again, the normal distribution in general, why do we have a whole chapter devoted to it? Well, it comes up a lot. There's a lot of values out there, a lot of data values that are normally or approximately normally distributed. Test scores, IQ scores, body weight among people. It comes up a lot, is what I'm saying, is what is the case. All right. So here, so let's suppose we have a test, and the test is out of 15. And let's say the scores, they're normally distributed. And in such a way such that the mean is 8, and the standard deviation is 2. So again, we have a normally distributed, what do you call it? Normally the data here, the scores on the test, they're normally distributed. The mean is 8, standard deviation is 2. We're going to apply the empirical rule, but before we do that, we need these calculations. Namely, we have the mean plus 1 times the standard deviation. I probably should have put parentheses here. I'm sorry I didn't. But we have the mean, which is 8, plus 1 times the standard deviation. 8 plus 2, which is 10. We have the mean plus 2 times the standard deviation. As you can see, that's 8 plus 2 times 2, 2 times the standard deviation, which is 12. 8 plus 4. 8 plus 2 times the standard, 3 times the standard deviation, which should be 3 times 2. So you have 8 plus 3 times 2, which is 14. 8 plus 6. Here's the same idea, except we're subtracting instead of adding. We subtract instead of add. All right? Now, so we get, subtracting, we get 8 minus 2, which is 6. 8 minus 2 times 2, right? 2 times the standard deviation, which is 8 minus 4, which is 4. 8 minus 2 times 3, right? The standard deviation is 2, 3 times it. So we get 2, 8 minus 6. And what the empirical rule tells us is that, I tried to graph it here. Let me just eliminate that. I'll regraph it. What we have here is that by the empirical rule, okay, 68% of the data is between 10 and 6. So if we go to 6 and 10, right, and let's say we decide to draw these, oh boy, my artistic skills aren't the best, bear with me. Okay. Anyone that's had me before knows that I have a hard time drawing things. But between 6 and 8, which again is the mean minus the standard deviation, and the mean plus the standard deviation, 68% of the data is in here, as you can see. So 68% of the data is there. Now, if you do the mean minus 2 times the standard deviation, right? We saw that's going to be between 4 and 12. 8 minus 2 times the standard deviation, 8 plus 2 times the standard deviation, that's going to contain 95% of the data. So let me shade that in as best I can. Okay, this is good. So between these two, you have about 95% of the data. Again, we keep subtracting and adding the standard deviation. And finally, between 2 and 14, which is 8 minus 3 times the standard deviation and 8 plus, you have 99.7% of the data. Yeah, I won't shade it in, but I will at least draw the vertical lines as best I can. Again, we don't have the data listed in front of us for whatever reason. However, we know it's normally distributed, so we know where most of the data is going to lie. So between these light blue lines here, most of the data will lie between them, 99.7%. I mean, there could be data values, there are actually past 2 and 14, right? Technically on an exam, this exam's out of 15, right? You can have students that get 100, 15 out of 15. I guess a student didn't study, so they end up getting a 0, unfortunately, or a 1. So it is possible to get those scores. It's just that they're very unlikely. So that's really what we're saying here. Let me just pause the recording.